Okay, so can I also tell you that all together in thermodynamics, this is called boundary work. And let me explain to you why it's called boundary work. In thermodynamics, the most simplest thing that we have is called a piston and cylinder device. Let me copy this down here, and then we'll talk. So let's talk about this first. So all of this table that we have just drawn is depicted here. Delta U equals Q plus W. So when heat is added to our system, this is our system, right? This is my system. The black ones are the boundaries. Imagine all the rest of the boundaries are adiabatic. Except for this part. I think these are called diathermal, right? Boundaries where heat is allowed to enter or exit the system. Okay. When Q is plus, what happens to delta U? Goes up. What happens to the temperature of my system? Good? Okay. Number two, when I do work on the system, that means I am pushing it in. What will happen to my delta U? What happens to my temperature? Make sense? This is the most logical way of remembering it. All you have to do is remember this table and this picture. Okay, on the other hand, when heat leaves the system, so when Q goes out of the system, number two, what will happen? What will happen to delta U? Goes down, right? That means the temperature of the system goes down. What about W? How will I make W decrease? Right? Expand. When I expand it, what happens to the delta U? Goes down. What happens to the temperature? Goes down. Make sense? That is what you have to remember. So the first part is plus W, compression, and the second part is minus W, expansion. And the simplest way of thermodynamics is what we will be dealing with a lot. Piston and cylinder system. Yes. Which, how much up? Oh. Okay.
Is there a scenario where you may have already explained this and I missed it, I'm taking that notes because late, where you get energy entering and yet the system still compresses as a result of it? So Q is positive, but W is also positive at the same time.
And then delta U goes down?
Wait, no, I'm trying to say, like, if you heat a system, that's energy going into the system,
Yeah.
and the system has to expand because of that. Like,
yeah.
It would shrink. I know what I'm trying to say. I'm just asking a stupid question.
Okay.
No, don't
it
answer.
will.
Don't you dare. Don't entertain my stupid question.
Excellent. Ooh, I should have more of those questions. Okay. So, are we good? May I move on? Okay. Now, the next thing I have to define is the system. So this is called a piston and cylinder device. It is the most simplest thermodynamical device, and all the engines that you will be dealing with in your projects are basically starting. This is the starting point for them. Okay, are we ready? Now, the next thing I have to tell you is that in this system, it is an idealized situation. Because as we will discover, in most thermodynamical problems, there are two options. Either we consider the idealized and cyclic transformations, or we don't do any calculations at all. That is going to be an engineer's problem on how unidealized things are. But as physicists, yay, we don't get to deal with those problems. So the idealized situation includes two things. One, perfectly frictionless surfaces. And two, completely adiabatic boundaries. Number three, perfectly insulating material. And how do I get away with making these bold claims? Nope.
You lie.
No, I don't lie. I keep it to my time under consideration. So perfectly frictionless, perfectly adiabatic, perfectly insulating. How do I get away with what I'm claiming? Small amount of time. So I get away with it by only considering these for the small time interval that I'm working on this. The next thing I have to tell you guys is this term. So we talked about work, right? And all I said was that there are two kinds. There were two kinds. What are the two kinds of work? Compression and expansion. Now I'm going to define another term that is called useful work. You press a button, what does an elevator do? It comes to you, right? Suppose you're on the third floor and you press the elevator. The elevator came up. But then you decided, no, I'm just going to take the stairs. Did the elevator do work? Was electricity wasted?
Yes.
But was there any useful work done? In order for it to have done useful work, what needed to have happened? Get on the elevator. Right? Does that make sense? So in order for useful work to be done, we need to move something, like a mass or something. So the idealized idea is, suppose you have, so remember we were talking about states 1, 2, and 3? What would be the most useful work that this piston does? So there are two weights on it, and it wants to get to state 3. If I take this weight and I call it one big weight, and I remove this weight, will it go to state 3 immediately? But was there any useful work done? Okay, now what's my next solution? Well, we can't heat the gas yet. So if I split my weight into 2, and in my first step, I take half of the weight away, and the piston shoots up a little bit. And then in my next step, I take all of the weight away. In which step was useful work done? So call this step 1 and call this step 2. Where was useful work done? In step 1, right? Now, what happens if I put this weight back on? Like here, I put one weight back on. What will it do? It will fall down to the state. What if I put another weight down here? It will fall back down, right? This kind of transformation is called cyclic. Cyclic. Where I could do useful work in some parts of it, but then by repeating it, I can bring it back to the original. So that's called cyclic. Transformation. They are also called reversible processes. And in thermodynamics, we are limited to these two conditions. So our choices are, number one, do calculations only for reversible processes. And number two, do no calculations at all. And this is where engineering comes in. Because engineers don't get that option. They actually have to build stuff.